Welcome back. We're about to do question 4 onward for dynamics worksheet number 5, the conservation of momentum. We have just finished doing question 2 and question 3, though I think the video of the last one might have cut out before the final part of D, and there is the solution. I think we got up to this point and then the video cut out. So there is the answer to that. Right, going to question 4 now. We're asked to calculate 3 things for this problem. A car of mass 900 kilograms is travelling 50 metres per second to the east, collides with a stationary phone box, a very light phone box. It only has 180 kilograms in it. And then, just like before, they have it entangled afterwards, after the collision. We are asked to answer 3 things. This question is trying to step you through it. I'm going to go directly down to part C because I want to start using just a single equation to find the phone box and its masses and so on. Right, so let's have a look at question 4. We know that the initial momentum must equal the final momentum. Okay, so using this, we know that the momentum of the car, the mass of the car times the velocity of the car plus the mass of the box times the velocity of the box must equal, now at the end, the mass of the car and the mass of the box become combined times the velocity of the mass of the combined mass, which is the car and box. We'll call it car box. Okay. Right, now I've got a full equation going on. I can then skip to finding this thing out. This is what we need to find over here, the final velocity of the whole lot. The question steps us through finding this section here and then finding this section and so on. So instead of doing that, I'm just going to go straight to C. Okay. So the mass of the car is 900. It is travelling at 15 metres per second to the east. The mass of the box is 180, but it's stationary, so it has a 0 velocity. Okay, we could have just put a 0 there, but I'm wanting to make sure that it has it's present in our formulas. And then we want the mass of the combined. At the end, the two things become 1. So adding that together, that's a 900 plus 180. And so that's 1,080. And this is what we want to find V. Okay. So now just simply putting that together, that's 900 times 15 plus 1, well, it's plus 0, isn't it? So I'll just put 0. We don't need to do that. Just do 900 times 15. Oh, it's the right one. So that's 1,300. That 13,500. Okay. That's 0, and it becomes 1,080 V. So solving that for V would equal 13500 on 1080. So it's this number here that's on my screen divided by 1080, and so it's 12.5 meters per second. Because it's a positive number, that would mean it's moving to the right or to the east as a positive number. Right, question 5. Question 5 is a whole series of questions about this, about bowling balls. So a bowling ball, which is 6.3 kilograms, hits a bowling pin, and the mass of the bowling pin is 1.6. Okay. Before the collision, the ball was travelling at 4 meters per second and the pin was stationary. After the collision, the bowling ball had not changed direction, because if it did change direction, we'd have to do 2-dimensional momentum, but now has a velocity of 2.8. So the first 3 questions here are calculating the momentum of the system and the momentum of the ball, and it's leading you through doing it. Okay. So we're going to go straight down to C, which is calculate the velocity of the pin afterwards, using just a single formula. So you can just skip these two if you wish and just go down to C. So let's work out how to do that with using a formula. So the momentum initial must equal momentum final. We know that. That's the conservation of momentum law. So the two masses is the mass of the bowling ball, and I'll just put as B, and the mass of the pin. Oops, that, which is P, and the velocity of the bowling ball and the velocity of the pin. Okay, so that's the initial. These are the two things which are there beforehand. At the end, we still have the mass of the ball, and we have the velocity of the ball, but this velocity of the ball has changed, so we'll just go velocity of the ball final, so BF, plus the mass of the pin and the velocity of the pin final, because these two numbers here don't match these two numbers here. These are the initial things, so I'll put the little I's there for initial if you want me to as well. Right, so putting in all the numbers from the problem now, the mass of the ball is 6.3 kilograms. And it is traveling initially at 4 meters per second, and we're going to assume it's traveling forward, and therefore forward velocity will be positive numbers. Plus the mass of the pin is 1.6, and we know that it's stationary because it's sitting there. We know what bowling's like. The pins are sitting down the bottom of the alleyway, and they're stationary. Right, now because there's no combining of masses, the mass of the bowling ball after would be the same. So that's 6.3. Now the final velocity of the bowling ball is now 2.8. Okay. And the mass of the pin is 1.6, but it has now changed. So it now has a velocity, which I'm just going to substitute as V. I don't need all this subscript going on here. I don't need that now. Okay, so this is the momentum. This is the initial momentum. This is the final momentum, and these two must be equal. And this sets us up with an equation that we can now solve. Working with those values, this is 0 here, so I'm just going to calculate 6.3 times 4, which is 25.2. And this would equal, on the other side, 6.3 times 2.8, and that's going to be 17.64. Okay, just check I've done that right. I think that's right. Plus 1.6V. Okay, this just gives us a very simple equation that we will solve. So 1.6V must be the subtraction of these two values. So that's 25.2 minus 17.64. And this is 7.56, and therefore V would equal 7.56 divided by, what's that value? 1.6, and that means 4.725 meters per second. Let me check if I've got that one right. Yes, it equals the answer, so I'm happy with that. Okay. Right, so that's A, B, and C all wrapped together in one little package. So the momentum, if you wanted to calculate the momentum of the ball system before, you would simply just do that section. If you want to calculate the momentum of the ball system after, it would be that section there. But we know that it has to equal this one, so it's the same number from there to there. And then we've done that. Right. D says, explain why we can be sure that work is done on the pin by the ball. So let's just remind ourselves what this is D now. What is work? Work is force multiplied by displacement. So this work, force times the displacement. So we have the bowling ball moving the pin. So there's my pin. Okay. So does the bowling ball put a force on this pin? And the answer is yes, because we know that this pin moves. Does the pin now move through a displacement? Yes, it does, because it moves. If it moves, it must be being displaced. So we know that there is a force because this pin moves and it is being displaced, therefore work is being done. So the bowling ball, these are 3 finger holes, does work on the ball. Okay, that's the reason why we can be sure of that. Okay. We want to calculate the work done on the done by the ball on the pin. Okay, now we don't know the force that is happening and we don't know the displacement through which the pin is being moving while these two become in contact. So we have to use another formula for work. And we know that work is equal to the change of kinetic energy of an object. In this case, we want the work on the pin. So this is the change of the kinetic energy of the pin. So that would be a half mv squared minus a half mu squared. Now, we know that initially the pin is 0. It's not moving. So we can simplify this to be just a half mv squared, because this part equals 0 up here. Okay, just put that in my formula so that it makes more sense. So this is the final velocity we want of the pin. So we just calculated that as 4.725. So it's a half times the mass of the pin, which is 1.6 times 4.725 squared. Working that out. So I've already got 4.725 on there, so I'm just going to square that value and multiply it by 1.6, whoops, 1.6, not 1.6 times 0.5. And so we get 17.86, which I'm going to round to, did I write? Yeah, I'll round that to 17.9, and work is measured in joules. Okay. Right, so that's calculating that. Going to F now. Contrast the total kinetic energy of the system before and after and explain your answer. So we're just going to contrast them. Actually, we've got to do the full one here now. So I'm just going to take out a piece of paper. So we'll do the kinetic energy before. Okay. So the kinetic energy, oops, that's off the screen there. So I apologize for that. Right. Now, the kinetic energy before will be the kinetic energy of the bowling ball plus the kinetic energy of the pin. And that would be a half mv squared plus 0, because the pin is 0 there, and this would be the initial velocity of the ball. So it's a half times the mass of the ball, which is 6.3, times it's 4, wasn't it, beforehand? 4 squared plus 0. So calculating that, which is 0.5 times 6.3 times 16. So it's 50.4 joules before. Okay, so there's the kinetic energy before. Let's work out the kinetic energy after. And we now know that the ball is a half times 6.3. Now the velocity of the ball after is reduced down to 2.8. So it's 2.8 squared, okay, because that's given to us in the question. So that's the ball, okay, plus the pin. Now the pin is a half times, it's 1.6 times the final velocity of the ball, which we got as 4.725 squared. Now we already have calculated that value. That's the work done. So that's already calculated as 17.9 joules. So we just got to add this part here. So putting those values in, you get 0.5 times 6.3 times 2.8 squared. So that is 24.7. plus 17.9. And that becomes 42.6 joules. Okay, so you'll notice that before it was 50 joules total, 50.4, and final after the collision we have 42.6. So kinetic energy is not the same before as after. So firstly, we can say that this is an inelastic collision. Okay. Now remember we have degrees of elasticity. Perfectly elastic would mean this number here and this number here are exactly the same. So it's only losing around about 8 joules. Okay, so even though it's inelastic because it's losing, it is reasonably elastic. It's not as if they're joining together and becoming combined together. Okay, so how much is lost? So the change of kinetic energy is, let's just calculate that as, let's put it over here so you can see, 50.4 minus 42.6, it's 7.8 joules loss. Okay, so we've lost 7.8 joules of kinetic energy. Remember, kinetic energy must be conserved, but kinetic energy doesn't have to be conserved because it is transferred or transformed. So where is this energy gone? We've lost 7.8 joules of kinetic energy. So it must have gone somewhere. It must have been transformed into something. We've already taken into account that 42.6 of these 50 joules has been transferred into the ball and the pin afterwards. So this has already been shared into this one here. So what's happened to this? That stuff there has been transformed. Okay, and what has it done? And you've all been in a bowling alley. We know that every time we bowl the ball down, you get that really large click sound, that really large collision sound. So mostly it is being transformed into sound and heat. Okay. So, and then you will also have some slight deformations, some deformities on the pin and the ball as well, some chipping and some irreversible damage. So we could also say it's not just sound and heat, but probably into deformation or deformity. Okay, well, yeah. So that's questions 4 and 5.